We'll continue our discussion on contraction mapping theorem. So we had, remember that the contraction mapping theorem, it said that T from X to X is a contraction if norm of Tx1 minus norm of Tx2 is less than, what did I use yesterday, alpha? What was the contraction coefficient? Alpha, beta, rho? I think I used rho. Norm of x1 minus x2. Rho is less than 1. Then xk plus 1 equals to txk converges to x star. And the x star is a fixed point. Actually, it's a unique fixed point. So it's not just, is a unique fixed point of T. So this was the result we proved in the previous class. So we start with any initial condition, x naught is in capital X. So I start from any initial point. I iteratively apply the same operator again and again. Eventually it converges to a point x star, which is a fixed point of T. In many areas of engineering, x star has some desirable properties. So we are talking about optimization. So in our case, x star is a stationary point. In the case of non-convex optimization, and x star is the optimal point in the context of convex optimization. And that's what we are trying to figure out. But in differential equations, x star would be the solution for a differential equation. In partial differential equation, x star would be the solution of a partial differential equation. In reinforcement learning / Markov decision processes, x star is a value function of the policy, and so on and so forth. So this theorem is something that you will see in a lot of different areas. And today we are going to study the convergence of this method xk plus 1 lambda k plus 1 equals to g xk lambda k and h xk lambda k. So I have the point and the Lagrange multiplier. I came up with some algorithm which uses operators g and h, which takes as input xk and lambda k. Assume that this particular operator converges. Assume this one converges to some point x star lambda star such that the gradient, so gradient x of g, gradient lambda of g, I think I'm right. Yeah. Gradient x of h, gradient lambda of h, this entire matrix evaluated at x star lambda star. The spectral radius of this matrix is less than 1. And what we were discussing is, if this condition holds true, and I start from a point x naught which is sufficiently close to x star lambda star, will I converge to x star or not? Actually, no. No, this is the conclusion. This is what I want to conclude. So Sorry, I have to change things now. So I know x star lambda star is a fixed point. The spectral radius of this matrix is less than 1. Then xk plus 1 lambda k plus 1 converges to x star lambda star. And remember, the operators that we are talking about today is g of x comma lambda is x minus gradient, sorry, alpha minus alpha gradient of x, and h of these are the two operators g and h that we are considering today. So this was what we did in the previous class. This was what I had mentioned as a result, which uses contraction mapping theorem. And we ended the previous class before we ended up proving this result. So now let's try to see why this result should hold. Any questions so far? Okay. So let's see. So I have a ball. So I draw a ball. The center of the ball is x star lambda star. I pick any 2 points. Let me call it x1 lambda 1, x2 lambda 2. And I need to show that this mapping g comma h is a contraction. I want to simplify the notation a bit. So let me call this y equals to x lambda, t of y equals to gx lambda, hx lambda, and I know that rho of gradient of t at y star is less than 1. Okay, so I'm renaming some variables a bit. Because I don't want to write long expressions. Okay, so I picked 2 points. This is y star, y1, y2. So what is t of y1 minus t of y2? Norm. This is equal to the norm of gradient of t at some y tilde. Y tilde is in between y1 and y2. y1 minus y2. This is mean value theorem. What should I do now? And what do I know? I know that rho of t of y star is less than 1. Oh, this, by the way, should be less than equal to. Okay. So here is one fact that I am going to pull from linear algebra. We haven't proved this fact, but this fact is an important fact for this proof to work. So let me define a matrix A is in Rn cross n. Row of A is less than 1. Then there exists a norm on Rn such that norm of Ax is less than equal to rho of A plus epsilon. Well, I need to put the quantifier here. For every epsilon greater than 0, there exists a norm on Rn such that A of x is less than equal to rho of A plus epsilon times norm of x. Okay, this is a result from linear algebra, and I am not going to prove this result, but you can find this result in any advanced linear algebra book. Now this is a general result. What I will tell you is if A is diagonalizable, right? So you could have a matrix A that is diagonalizable, in which case you don't really need to have this epsilon. So in general, A could be non-diagonalizable, in which case you will have this epsilon term here. But if A is diagonalizable, which means that you can use the eigenvectors of A to diagonalize A, you can come up with a similarity transform that diagonalizes, then in that case you don't need this epsilon. You can actually come up with a norm such that that condition holds. But we'll use this particular form. Okay, so in my case, my A matrix is going to be gradient of T evaluated at y star. That's my matrix A. I don't know whether this particular matrix is diagonalizable or not. So let's assume I picked a norm such that epsilon equals to 1 minus rho of gradient of T at y star over 3. So this epsilon is strictly greater than 0. What should I do now? Okay, so let's think about it. So this is my matrix A. I am picking an epsilon greater than 0 that gives me a norm on the space Rn such that A of x is less than equal to this. So let me write it down. So I'll have norm of T of y star times y1 minus y2 norm is less than equal to rho of gradient T y star plus epsilon times norm of y1 minus y2. So I have this particular result from this theorem. I get this result. Is this term less than 1? Is this term less than 1? So remember, I picked epsilon carefully. Okay, so if I picked epsilon like this, then this particular term is certainly less than 1. Okay, wonderful. So I have this result from using the theorem, but remember, this is what I want to prove. This is what I want to prove. And I have this gradient of t of y tilde. So it's not quite y star, but what do I know? I know that this y1 and y2 are close to y star. So in particular, this y tilde is also close to y star. And all I have to figure out how close to y star should I pick, right? So here is the idea. I'm going to pick the radius of this particular ball, whatever the r is. I'm going to pick the radius such that the matrix norm of gradient of ty is less than equal to rho a plus 2 epsilon for all y in ball of radius r around y star. Okay, so a lot of different results that are coming together to prove this particular result. So what I know is matrix norm is a continuous function of entries in the matrix. I know that these functions are differentiable and infinitely differentiable and continuous. As a result of which, if I move from y star to a point in the vicinity of y star, my matrix norm is always going to be bounded by this particular value. And I know that this particular value is also less than 1. This value is less than 1 because of the way I have picked this epsilon. So this implies that if I go back to this particular expression, this norm is less than 1. This is y1 minus y2. I'm picking y1 and y2 within a ball of radius r around y star. So if I start sufficiently close to x star lambda star, this iteration is a contraction map. I mean, this map is a contraction map, as a result of which eventually I'll converge to x star and lambda star, which is the desirable point. And the reason for doing this proof in the class is to introduce you to some of these tools and techniques that are used for analysis of algorithms. So no matter what, so I know some of you are graduate students, some of you are undergrads, but no matter which field you pick up, you will eventually be using optimization algorithms, and at some point of time you will encounter a situation where you have to prove that the algorithm is converging to a point that is desirable, and the way to prove that result is to use the contraction mapping theorem in almost all the cases. This is the result that you will be using. And what I have noted down here is a way to go around proving this particular result, or at least understanding the proof. Even if you are not proving it, somebody else might be proving it in a paper or in a book, and you can understand what the argument there is going to look like. Okay. Now there is one question that I really want to emphasize. So remember, I have two hyperparameters. All of you know what hyperparameters are? Hyperparameters for an algorithm. So we have two hyperparameters here, this term alpha and this term c. Okay, I can pick whatever alpha and c makes sense to me, which leads to convergence of the algorithm. And I want you to think a bit about what does alpha and c have to do with this contraction mapping result. Okay, so you have done a lot of optimization, you've implemented a lot of optimization algorithms so far. You've also done one example when you did this momentum method and you plotted the spectral radius of certain matrices, and you tried to figure out what's the best hyperparameters or step sizes are, which leads to convergence, the fastest convergence of that particular algorithm, right? So what exactly were we trying to do in that particular situation? So if you think about it, this alpha and c influences the rho of gradient of Ty star. This particular gradient, this particular rho, which is the spectral radius of this matrix, that's influencing the size of epsilon that you're picking. This epsilon is in turn changing the value of r that you can pick here in this particular place. So in particular, what I'm saying is, if you pick alpha and c, that influences the rho, which influences the epsilon, which influences the r. Rho tells you how quickly the algorithm is going to converge to the optimal solution. So remember, this is eventual convergence, but if you stop at time k equals to 100, you could be far from x star or you could be close to x star. And if rho is close to 0, you will get to x star very quickly. If rho is close to 1, you will get to x star after 1,000, million, billion iterations. Okay, so when you are, let's say you are training large language models, your xk, what's the dimension of this? 1.8 trillion. Okay, that's the dimension. How many iterations do you need to do in order to get to x star? X star is the optimal solution. X star is the optimal weights of the large language model. So you are in a 1.8 trillion dimensional space. You have this gradient operator, gradient descent, steepest descent operator that you are applying again and again. You want to pick your hyperparameters. You want to pick your network architecture, the neural network architecture, as well as your step sizes in a way that rho is as small as possible. Nobody knows what the smallest rho is going to be, but you have to make your educated guess based on multiple runs of the simulation. You want rho to be as close to 0 as possible. And then if it is close to 0, this epsilon would be very large. And this epsilon is very large, it means r is going to be very large. So you can misspecify, you can be far away from y star and you can still converge to y star. On the other hand, if your rho was close to 1, your epsilon is very small, consequently your r is very small, which means you have to stay close to y star and then you have to try and converge to the optimal solution. So again, going back to the large language model example, when you're doing fine tuning, what exactly are you doing? You're starting very close to y star and you're trying to converge to y star. So that's what fine tuning means. When you are, but when you are training a large language model from the very beginning, you start with random initial weights and then you are training the language model. In that case, you're starting from very far away, and then you want to pick your hyperparameters, alpha and c, somewhat conservatively, so that rho is as small as possible, rho is as close to 0 as possible. Okay, so roughly in the what I'm trying to make a comment on is the hyperparameters or the step sizes that you pick influences the region of convergence of these algorithms, and the way it changes the region of convergence is because rho could be close to 1 or close to 0, and that could influence the radius over which you are converging. Okay, so that's something you need to keep at the back of the mind. So whenever I'm trying to tell you that you pick a specific step size, the algorithm diverges, you pick some other step size, the algorithm converges, or some algorithm would converge faster if you pick a different step size. All of this is basically pointing to making sure that this rho is as small as possible. I mean, ideally you want to pick step sizes that makes this rho as small as possible, and then you converge to the optimal solution. Okay, so that's something I want you to keep at the back of the mind for the rest of your life, because some of you, I'm assuming, would be applying algorithms of this type on embedded devices in vehicles, in battery packs, in air conditioning systems, in sewage treatment plants, in energy systems, and so on and so forth. And these hyperparameters are going to influence how quickly or how how much time you're going to take in order to converge to the optimal solution. Okay, any questions so far? Okay, so I think we are at the end of the discussion on static optimization problems. So I'll just do a very quick recap of whatever we have done so far. Meanwhile, if you have any questions on this material, please feel free to ask me right now. Okay, so initially we wanted to solve problems of this type, and we said that my algorithm is going to be xk minus alpha k dk gradient of fxk. Then I said I want to minimize f of x such that x is in a convex set. And then we had a whole bunch of algorithms, gradient based algorithms. We had conjugate gradient method, conditional gradient method, manifold suboptimization methods, and so on to solve problems of this type. Then we said, well, I have problems of this type. How do I solve problems of this type? And then we talked about Lagrangian methods. Generally speaking, we considered the case where this x was Rn, but we also had some situations where x was a convex set. But nonetheless, there were 4 algorithms we studied for solving problems of this type. It was barrier method for inequality constraint problem, augmented Lagrangian method for equality constraint problem, penalty method for, or sequential quadratic method for the case where you have both equality and inequality constraint. And then we talked about the Lagrangian method, which is what the proof is about, where you had a equality constraint problem but no inequality constraints. There are, of course, valid ways by which you can convert this problem to equality constraint problem, where you are minimizing over x and z, h of x equals to 0, g of x plus gj of x plus zj square is equal to 0. Right? So you can solve either this problem, which is equality constraint problem, or you can solve this problem which has inequality constraints as well. The 2 solutions are going to be the same. Okay, so now we have studied how to solve this problem, how to solve this problem, and how to solve these kind of problems from arbitrary initial condition. You can pick your x anywhere in the space, and by an appropriate choice of step size, by an appropriate choice of the positive definite matrices, and so on, in all of these cases, there were always certain hyperparameters that you can optimize in order to get to the optimal solution. Okay, so what's next? The next topic that I want to cover, which will go all the way until the end of the semester, is dynamic optimization method. Okay, so this is called static optimization. This is static. Okay, so in static optimization, I'm given a function, I'm given a bunch of constraints, I need to optimize the function and figure out what the solution is. Dynamic optimization is slightly different. So now you have a system, it's a dynamic system, it has a state and it has an action. The only way you can influence the state is through your action. So let's come up with an example. I'm driving a vehicle. My position and velocity of the vehicle and the heading angle of the vehicle, that's the state of the system. And what are the actions of As a driver, what are the actions I'm taking? I'm changing the steering wheel. If you're driving a manual car, you're changing the gear. Otherwise, you're applying the brake or you're applying the acceleration. Okay, those are the 4 actions that you typically take in a context of a dynamic, in the context of driving a vehicle. So the only way you can change the state of the vehicle, the only way you can change the heading, the position, and the velocity of the vehicle is through your action. You can't just pick a specific position, velocity, and heading. You can take an action and you might be able to achieve a certain velocity and a certain position and a certain heading. So the question then becomes, how do you optimize your actions in order to optimize certain cost criterion for that particular dynamic problem? So in the case of driving a vehicle, you might want to optimize the fuel consumption. Okay, that's a possibility. If you're driving an electric vehicle, you might want to optimize the range of the vehicle. By driving appropriately, you can change the range of the vehicles. How many of you have driven an electric vehicle before? 2 people? Okay. So how do you increase the range of the vehicle through your driving habit?
Apply as little torque as possible to maintain speed.
To maintain speed, apply as little torque. Yeah.
Take as much regen back into the
right.
battery.
How does that change the behavior of you while you are driving the vehicle?
Well, if you brake more aggressively, more frequently, you can get more regen and more energy back to the
Are you saying more aggressively or less aggressively?
More. You take more torque.
So if you apply brake more aggressively, you can save all that energy. If you apply less aggressively, you won't be able to save the energy.
As long as it doesn't go over the limit of the torque that the motor can provide.
Right.
Yes.
Right. Okay. So there are certain limits in the electric vehicle system. What is the torque that the motor can provide versus what is the regen that the motor can provide? And so within those limits, if you're able to brake and if you're able to accelerate, you will be able to increase the distance that your car can go. The other small thing that you can change in your vehicle is air conditioning system. You can change the temperature of the air conditioning system in order to save further energy. So there are some actions that seems to be saving energy, that seems to be extending the range of your vehicle. And the way you do that is by picking an appropriate set of actions at every point of time. Right? So the theory of dynamic programming or the theory of dynamic optimization essentially tries to study what are the actions you can take in order to optimize whatever metric you want to optimize. So if you think about it at a university level, I think university might be paying $1 million a month or maybe a little bit more than that for electricity cost. Okay, and so if you can save 5% electricity, you are saving $50,000 a month for the university, right? And that's the cost of a graduate student. Okay, so then the question becomes, what are the actions available in order to optimize the energy consumption of the buildings in the university? So can someone tell me what actions would you take if you were responsible for optimizing the energy consumption of buildings across the university? University has about 500 buildings all over Columbus. What actions would you take to optimize the electricity? Yeah.
You could turn off the lights in the classrooms.
Wonderful. So you will put some motion sensors in the classroom and you can turn off the lights whenever there is no motion inside the classroom. Perfect. What else would you do?
I mean, you could do something similar, like, I don't know, turn off the air conditioning.
Turn off the air conditioning. You cannot really turn off the air conditioning. That's the problem. But you can do something else. Yeah.
Replace the bulbs with more efficient bulbs.
Okay, replace the bulbs with more efficient bulbs. So we have whatever, maybe incandescent light and we want to change it to LED lights. Perfect. Okay, what else can we do? That's a very capital intensive project, by the way. You need a lot of money to do that. Yes.
Instead of just turning off the AC, you can adjust the high and low.
That's right. So all ACs like we have here, so you can adjust the temperature setting for the particular AC. So in the heat, you can increase the temperature, the set point of the temperature to 74 degrees Fahrenheit. If it is winter, everybody is wearing a jacket or something. And then you can reduce the temperature setting to 68 or something, and then you will be able to save a lot of energy for the university, right? So in every dynamic setting, there is some actions that are available to you. There is some performance metric. Typically, the performance metric is going to be try to save lives, try to save money, try to reduce risk, right? Those are the typical performance objectives, or maximize revenue or something like that, right? So those are the kind of performance metrics that people tend to optimize whenever they are solving a dynamic problem. Okay, so how do we set up the dynamic optimization problem? So I'm going to start with the simplest setting, and then over time we will make things more complicated. So how do we formulate the dynamic optimization? We have what is known as a state update. By the way, just so you know, my research is about dynamic optimization. I don't do much on static optimization, but I teach it. But my work mainly focuses on dynamic optimization. So you have a state update equation, which is xt plus 1 equals to ft of xt comma ut. So this is known as the state transition function. Xt is known as state at time t. Ut is known as action at time t. So sometimes people call it action, sometimes people call it control. It's the same thing. So state at time t, action or control at time t. Ft is the state transition function. So if this is your current state, if this is your current position, velocity and heading, you take a steering angle, braking or acceleration, what exactly is your new state going to be? What's your new position, new velocity and new heading looks like? You have a cost function, Ct of xt ut. This gives you a value in R. So Ct is known as the cost function. Ct is evaluated at xt and ut. You get a value in R, that's your cost. So this is the cost of energy. This could be negative of the revenue. This is the total energy consumption of the vehicle, or whatever the current energy consumption of the vehicle. So you could either have a dollar amount, or you could have kilowatt amount, or you could have some other amount that quantifies at the current state and the current action what is the cost that you are incurring. And the goal is the performance index in this particular class. We are going to look at the finite horizon setting. So summation j of u0 to u capital T equals to Ct plus 1 xt plus 1 plus summation t equals 0 to t Ct xt ut. So this is known as a terminal cost. This is known as the horizon length. How many of you have seen this kind of formulation before? I'm sure the car people have seen it. Outside of car, anybody who has seen this before? You have seen it? Do you work in which area? Controls? Okay. So you have seen it in controls. Anybody else? No? Okay. Let's look at different examples of this particular problem. So we did talk about the car example. Anyone remembers SpaceX rocket that came back into the launch pad? So it went all the way up and then came back into the launch pad. What are the control actions there? What can the rocket control? Anyone remembers? Sorry? Thrust. What else? What else can it control besides thrust? Yeah.
Roll, pitch, and yaw.
Yeah, roll, pitch, and yaw of the rocket. So either you move the thrusters in some direction, so that way you control the roll, pitch, and yaw of the rocket. By the way, roll, pitch, and yaw would be the state, not the. So you have position, you have three-dimensional position, three-dimensional velocity, and then you have roll, pitch, and yaw of the rocket. So you have nine-dimensional state there. And the actions would be, of course, the thrust, but either you have thrust vectoring, which means you can move the thrusters in a specific direction, or you will have fins or ailerons, which you can move in specific directions in order to change the roll, pitch, and yaw of the rocket. Okay, so we have very high dimensional state, very high dimensional action. If I remember correctly, it had four different rocket engines, the SpaceX thing. So it had one main engine and then three different other engines, and you could turn off the other engines if you wanted to in order to change the position or the heading of that particular rocket. Okay, so you have a bunch of actions and a whole bunch of states in that particular problem. What is the running cost of that particular rocket? What is it that the rocket is spending at every point of time? Fuel. Okay, so at every state, at every position, velocity, and attitude, if the rocket uses a certain amount of fuel, if the rocket takes a certain action, then it's going to cause a certain amount of fuel to burn. What's the terminal cost? What is it that the terminal state of the rocket should satisfy? Yeah.
I mean, the terminal cost, like the rocket landing.
Yeah, the docking and landing. Okay, so you want the state to satisfy a specific criteria, so it should dock and land at a very specific position, and that's your terminal cost. Okay, so you want the rocket to land at a specific position, so distance of the rocket with the orientation and position that the rocket should be has to be as small as possible, ideally within millimeters or within centimeters, and not within kilometers. Okay, so you have a huge terminal cost there, you have a huge running cost there, you have a very complicated system there, dynamics there, and you want to optimize, you want to figure out what's the minimum set of actions you need to pick to be able to land safely at the position where it's supposed to land, while minimizing the fuel that it's needed to complete the mission. What is this capital T going to be in the case of rocket? So let's think about it. What's the one time step, time t to t plus 1? What's that going to look like in the rocket setting? I'm assuming it's going to be 100 milliseconds or 500 milliseconds. Okay, t to t plus 1 probably is 500 or 100 milliseconds. What's the total length of the mission of the rocket? Probably half an hour, maybe 1 hour. Okay, let's consider maybe it's 1 hour. So I have t equals to 3600, and let's say the one time step is 100 milliseconds. Then 3600 seconds divided by 100 milliseconds. What do I get? 36,000, right? Roughly. So a 1 hour mission of the rocket is 36,000 time steps, and you need to optimize this problem. You need to optimize this whole thing with 36,000 different variables. So each UT what was the dimension of U? Let's say it is equal to 4. So U0 to UT is in what dimension? 4 cross 36,000. Right? Roughly. I'm not being very precise here. But if the dimension of U is 4, if I have 4 different actions to pick at every point of time, I have 36,000 time steps. I'm doing an optimization in, what's 36 cross 4? 144 maybe. Okay. I think it is 144. So this is R raised to 144,000, right? So very large number. So you have to do an optimization over such a large number in near real time. Okay. Rocket is very, very risk sensitive. What's the cost of one rocket? Maybe $50 million. And if you are not able to do this optimization in near real time, you lose $50 million. Have you seen how $50 million gets burnt in the space? I'm sure you have seen a lot of failed launches that SpaceX has done. So you can literally burn $50 million in a matter of a few seconds if you don't do this optimization right. Okay, so it's important. Let's look at a hybrid vehicle, plug-in hybrid vehicle. So you have a large battery pack. The battery pack has a state of charge, and it has the amount of fuel. Every time you take an acceleration or braking action, you are losing energy or gaining energy depending on what kind of action you are picking, and your position and velocity of the vehicle will also change. And of course, the goal is to minimize the total energy cost of the vehicle for going from point A to point B. You could have a rocket that's going all the way to Mars. Okay, that's a completely different mission. So SpaceX rockets are supposed to go, get the vehicle to some position, get the satellite to some position in space and then come back. Okay, so in 1 hour or maybe in 2 hours, they'll be able to complete the mission. If your rocket is supposed to go from Earth to Mars, how much time do you think it takes to go from Earth to Mars?
Probably like a few months at the very least.
Yeah, few months for sure, but how many months?
3%.
It takes about 6 to 8 months to go to Mars. Okay, so you are essentially looking at this capital T, which is a very, very large number. But the funny thing is, for most of the time, you don't have to do any computation. The satellite is just coasting in the space, but then you have to turn on everything as soon as it's closer to Mars, and you have to turn on everything when it's closer to Earth. But rest of the space, it just has to coast around. So even though the T is very large, for most of the time, the running cost is 0. And then there is a huge running cost at the beginning and a huge running cost at the end. Nothing else in between. Okay, so you have a whole variety of different dynamic optimization problems. Different problems will have different dimensions of the actions, different horizon length depending on the mission. One time step could have different meaning from one problem to another. And what else? Your state transition function could be highly nonlinear or it could be linear, depending on the situation. Okay, so this function could be very complicated or could be very simple. This function could be very complicated or could be very simple. Terminal cost could be very elaborate or it could be very simple, right? And then you have so many other things to think about. Robotics is, by the way, another application. Anyone taken 5463 in ECE? A couple of people, right? So robotics also, you want to, generally speaking, in robotics, you are not really trying to optimize energy, but you are trying to optimize the trajectory of the robot, because you don't want the robot to start slapping people walking on the road, right? Or start bumping into cars and so on. So the cost there comes from avoiding the obstacles or avoiding a moving target. So that's where robotics, in the robotics application, this cost is not the energy, but trying to avoid bumping into people or bumping into objects and then destroying yourself. Okay. Anyway, so this is the problem statement. And here is what I want to solve. Goal. find, or I should say not find, but compute U0 star UT star that minimizes J of U0 UT. How should we solve this problem? Okay. So there is some goal, there is some mission that I need to achieve. I need to go from point A to point B. I need to send a rocket to space and then make it come back. I need to send a rocket to Mars. There is some mission that everybody agrees that that mission is an important mission. I have a state transition function, and somebody from physics, chemistry, biology department has given me what the state transition function looks like, or mechanical engineering, or aerospace engineering, or electrical engineering, right? So depending on whether you have a motor or you have an electric system or a mechanical system, the corresponding people will come up with the state transition function. Depending on the mission that you want to achieve, you will have somebody will define the cost function. And as an optimizer, your job is to talk to all these people, get all of these maps, put it in MATLAB, and then solve this problem. Okay? And in the next class, I'm going to talk about how exactly are we going to solve this problem. And there are many ways by which you can solve this problem, or there are many, the solution will be the same, but there are various ways to look at this problem. So we'll try to look at this problem and we'll try to solve it in the subsequent classes. So a lot of theory that we are going to talk about from now until the end of the semester, just trying to solve this particular problem. Okay, thank you so much. See you.